Guys, 5.2, we're talking about rational exponents and radicals, and probably more so about the radical aspect of things rather than the rational exponent part of things. So last class we talked about rational exponents, and we learned the connection between a rational exponent, a fractional exponent, and a radical, okay, and how we can convert in between both. Today we're going to dive in a little bit more to both of those, but spend a little bit more time on square root. So our objectives today are to use properties of rational exponents to simplify expressions with rational exponents. Sounds redundant. And to use properties of radicals to simplify and write radical expressions in simplest form. So example 1 here, it says use properties of exponents to simplify the expression. So we're doing the same things that we were doing on the board, except now we're going to have fractional exponents. So what do I need to do to my exponents here? What if this was 7 squared times 7 to the 4th? I would add my exponents. So just because they're fractions, it doesn't change what we need to do. We need to add them. Now when I add fractions, have to have a common denominator. So a common denominator between 4 and 2 is going to be 4. So I'm going to make this 7 1/4 times 7 2/4. Well, that's going to be 7 and, got to add 1/4 and 2/4, 3/4. Okay, we're going to leave it like that. Now, could I call that, or again, this is my power over my root. Could I call that the 4th root of 7 cubed? I certainly could, but I know that 7, there isn't a perfect 4th root of 7, so it doesn't help us to do this. So I think that's how we should leave our answer. But we need to understand that those two things are the exact same thing. Okay, what do I need to do to my exponents in this situation? We can multiply them. So this is going to be 5 to the, well, 3 over 1 times 1 over 2. That's going to be 3 over 2. When you multiply fractions, multiply the numerators together, multiply the denominators together. So that answer there would be 5 to the 3/2 power.
You wouldn't, just only multiply the exponent of the 5 or whatever, or multiply 3.
Yeah, if I had like this, I think we were just doing this. If I had this, I would just multiply the exponent.
If there was like a 2 in front of the x, though, what do you do?
Yeah, now you're talking about completely different. If there was a 2 here, now the 3's got to go to both. Yes?
Wait, so why are we doing that with 5 now?
Say it again?
Why are we doing that with the 5?
Okay, because the 5 is replacing the x. So when we have exponents, we have a base and we have a power. Well, in this case, the base is 5. In this case, the base is x. So it might be a little bit different now that we have an actual number there, but that is acting as our base. Great question. Okay, third one here. What do we got to do with my exponents? If I had x to the 5th over x squared, what do I do with my exponents? We subtract them. Now, I've talked about canceling, which works in certain situations, but we should actually subtract. Now, what's my exponent here? It's 1, but again, if I'm going to subtract fractions, I should have a common denominator. How do I write 1 in terms of having a common denominator of 3? 3 over 3. Would you guys agree with that? 8 to the 1st power is the same thing as 8 to the 3 over 3 power, because 3 over 3 reduces to 1. Well, now I can subtract. What's 3/3 minus 1/3? 2/3. 8 2/3. Okay, and let's change this. Instead of making this a 9, make it an 8. So it's 9 to the 4th over 8 to the 4th.
We're officially changing that to 8 over the 4th.
Now, if you want to simplify this one, Sam, is that what you're asking?
Yeah.
Sure. So this is my power and this is my root. Can we simplify that?
But doesn't the 2 8s, don't they cancel each other? Or
What's that?
don't they cancel each other, the 8s?
No, because those are our bases. That's our base. Okay? Now, power over root, what's the cube root of 8? So if I rewrite this, isn't this the cube root of 8 squared? Oh, what's the cube root of 8? 2. What's 2 squared? 4. So I think our most simplified version would be 4. I think so, yes. I didn't recognize it right away. But yeah, that's the most simplified version. It didn't help us to do that over here because I don't know, again, power over root, the square root of 5 isn't a nice number. The, let's see here, the 4th root of 7 isn't a nice number. Yes?
So you would only like put it like how you put it to like 4 if it came out as
Yeah, we would probably only want to do that if we can do anything with it. Does that make sense? If we can actually, hey, take that info and simplify it. Now, would you guys agree that we've got a negative exponent out front? We have a negative exponent. So whenever we have a negative exponent, we should, outside, take the reciprocal. So I'm going to make this 8 to the 4th over 9 to the 4th. And then this becomes a positive 1/4 power.
you multiplied that. I'm lost. Did you multiplied that fraction? Is that what you're saying?
So if, like I talked about in the bell ringer, that if I have, let's just say I've got 5x over 3, and this is to the negative second power. If I have a fraction in a negative exponent, really if I have a negative exponent out of anything, I should take the reciprocal right now. Well, just like when we have a negative exponent, we cut, edit, paste, and move it to the bottom, we're doing the same thing. So I'm going to flip this and make this 3 over 5x to the positive second power. So all I did was I flipped it and made a positive exponent. Now, this 1/4 needs to go to both the top and the bottom. Now, what's 1/4 times 4? What's 1/4 of 4? That's just 1, right? If I have 4 cookies and I say, hey, Tristan, you get 1/4 of my cookies, I'm going to give Tristan 1 cookie. So this is going to be 8 to the first power and 9 to the first power. So the answer there would be 8/9.
Dang, that one was easy.
Questions here? Okay, now we're going to start talking about some more radicals. And we have 2 properties that we can use. The first one is called the product property. Product property says this. If I have a root, in this case an nth root, of 2 things being multiplied together, I can separate that into the nth root of A times the nth root of B. And that also kind of works the other way. That if I'm taking the nth root of 2 things, that's this separately, that's the same thing as taking the nth root of them times together. So for example, if I have the cube root of 4 times the cube root of 2, well, that would be the same thing as the cube root of 4 times 2, which is 8. What's the cube root of 8? 2. So in this case, it helped us to multiply these cube roots together because they gave us a perfect cube. The next property is called the quotient property. And so if I'm having the nth root of a fraction, let's say a over b, that's the same thing as taking the nth root of the numerator divided by the nth root of the denominator. So, for example, if I have the fourth root of 162 and the fourth root of 2, what's 162 divided by 2? 81. Is 81 a perfect fourth root?
Yes, I changed my mind.
I think it is. So I can rewrite this and say the fourth root of, I don't know why I wrote it like that, the fourth root of 81, because actually let me rewrite that, I'm sorry. Fourth root of 162 over 2 equals the fourth root of 81. Well, that is 3.
Changed my mind, Hannah. Okay.
All right, let's get into some examples. So right now, by itself, I don't know the third root of 12. It's really not nice, okay? And really, the third root of the cube root of 18 isn't really nice and neat either. Let's check. 12 times 18, what is that? 2 what? 216. Is 216 a perfect cube?
Yes.
It is. What is that? It's 6. 6 times 6 times 6 is 216. So in this instance, it actually helps us to combine them because then it becomes a perfect cube. Same idea here. If I look at my numerator, hey, fourth root of 80 is not really anything special. Fourth root of 5 is nothing really special. But if I do 80 divided by 5, 16. So I can do the fourth root of 80 divided by 5, which is the fourth root of 16. What's the fourth root of 16? 2. Okay? Now let me talk a little bit about, does this have to be plus or minus? And the answer to that is no. And really, you remember how I said, hey, if you put the square root sign in, you have to do plus or minus? It's kind of the same idea here. I don't need to count this as plus or minus unless we put the radical in ourselves. Okay? So the 2 there would be our final answer. Okay, now it says we want to write things in simplest form. Now, why do we want to write things in simplest form? I should say, how do we recognize if things are in simplest form? All right, we don't want to have, in this case, in this first one, which we've already done, we don't want to have, if it's square root, we don't want to have any perfect squares that are a factor of 32. So what's the largest perfect square that's a factor of 32? 16, right? So I can break this up into the square root of 16 and the square root of 2. Well, the square root of 16 becomes 4. So 4 square root of 2, that's our final answer. Now that shouldn't be new whatsoever because we did that a bunch first semester when talking about quadratics and all that stuff. Okay? But that idea carries over to this next idea. Okay? So we want to do the same thing, but now instead of looking for perfect squares, I'm going to be looking for perfect cubes. Okay? So hopefully we have an idea of our perfect cubes. If we don't, we should probably write them out. But I'm looking for my largest perfect cube that's a factor of 135. So again, perfect cubes are 1, 8, excuse me, 27, 64, 125, 216, and so on. Is there one of those that's a factor of 135? Someone say 27? What's 135 divided by 27? 5. Okay, so I'm going to break that up and say, hey, the cube root of 27 and the cube root of 5. Because the cube root of 27 is times the cube root of 5 is the cube root of 135. So I can just break it up. Now the cube root of 27 is 3. So I have 3 times the cube root of 5, and now that is in simplest form. Same idea here. I'm looking for the largest fourth root that's a factor of 162. Did I have 162 earlier in the lesson?
I think so. Yeah.
I did.
81.
Is 81 a perfect fourth root? It is. And 81 times 2 is 162. So I'm going to break this up into the square root of square root of 81 times, not square root, fourth root of 81 times the fourth root of 2. Because 81 times 2 is 162. And now the fourth root of 81 is 3. So 3 times the fourth root of 2 is our final answer.
Why do we leave the fourth root of 2?
Say that again?
Why do we leave the fourth root of 2 as we can't bring it down anymore?
Because I can, just like over here in this first example, we found my largest perfect square, since it's square root, which is 16. Well, the square root of 16 is 4, but we've got this leftover part that's just not going to simplify any further.
Okay.
So we need to keep that on. Okay? Now, the square root of a fraction. Okay, the square root of a fraction is really the square root of the numerator over the square root of the denominator. Okay? Now, when we have a fraction, we compare things using the denominator. Okay, so for example, I'll say, hey, this classroom is like the boy to girl ratio or fraction would be like, let's just say 10 to 22. There's 10 boys, not girls. I'm saying, let me start over. Boys to students would be like 10 to 22. We have to have the 22 part. Okay, we have to understand what the whole is to have an understanding of what the numerator stands for. So a rule in math is that we don't like to have the square root in the denominator. Okay, so we have a process called rationalizing the denominator. Because the issue is the square root of 3, everyone type square root of 3 in your calculator, go. What do we get there?
1.732.
And that number goes on forever. It's never going to stop. So how can you have that in the denominator? It's kind of hard. Okay, so what we need to do is get that out of the denominator. So here's our rule. If it's square root, and really in this class we're only going to do square roots, I need to get the square root of 3 out of the denominator. Now check this out. I can multiply a fraction on the top and bottom by the same number. Now what we want to do is multiply by whatever's in the denominator. Why do I want to do that? Yeah, in the denominator there, what's the square root of 3 times the square root of 3? It's 3. Okay, here's a shortcut. Square root of 3 times square root of 3 is 3. Square root of 47 times the square root of 47 is 47. So in our denominator, I'm going to have 3. And then in my numerator, I'm going to have square root of 21.
Well, what do you know about that?
So now it's rationalized because the denominator is a whole number. It's not a square root anymore. So we never want to leave a square root in our denominator. We talked about this in geometry last year, just a little bit. Now this next one is the square root of 5 over the square root of 18. Now, before we do that, would you guys look at square root of 18 with me? Is there a perfect square that is a factor of 18? It's 9, right? So what I want to do is I want to simplify the denominator before I rationalize the denominator. So I'm going to break my denominator up, and this should be equals. This should say equals the square root of 5 on the numerator. And this, I'm going to break this up into the square root of 9 and the square root of 2. What's the square root of 9? 3. So now if I go down here, I'm going to have the square root of 5 divided by 3 square root of 2. So this part, I've done nothing to I can't say that. I've simplified it. I've done nothing to rationalize it. I still have a radical in there. Instead of radical 18 now, it's radical 2. So now, to get rid of this 2, what do I need to do? Times by the square root of 2, top and bottom. So now in my numerator, what's the square root of 5 times the square root of 2? Yep, square root of 10. And then in my denominator, I'm going to have 3 times, square root of 2 times square root of 2 is 2. 3 times 2 is 6. Now, some of you might be asking, well, Mr. Cole, can I just take the square root of 5 over the square root of 18, and can I just multiply by the square root of 18? We certainly can. Okay? But if I get this, I'm going to get 18 in the denominator, right? What do I get in the numerator? What is it? 90. We need to ask ourselves, is there a perfect square in the numerator that's a factor of 90? Wasn't it 9?
Yes.
So now I'd have to simplify the numerator and call this the square root of 9 and the square root of 10 over 18. What's the square root of 9? 3 square root of 10 over 18. And now I can simplify these. So take a 3 out of each. So it doesn't matter whether you simplify first like I did here, or you rationalize first like we did here. But you're going to get the exact same answer. Okay, again, isn't there a square root in the denominator? But what's different about this one?
Addition in the bottom.
Yeah, addition, or it could be subtraction, but I'm adding or subtracting things in the denominator. So what I need to do is we need to multiply by what we call the conjugate. The conjugate is the same thing except the opposite side. So I want to multiply the top and the bottom of this fraction by the conjugate, which is 5 minus square root of 3. Now, why would we do that? You'll see here in a second. Because what's our goal in doing this? What, Autumn? Absolutely, get rid of the square root. Okay? So I'm going to, in the numerator, I'm going to distribute 1 times 5 and then 1 times negative square root of 3. That's just going to get us 5 minus square root of 3. And then in the denominator, I need to FOIL. So 5 times 5 is 25. 5 times negative square root of 3. Well, that's going to be negative 5 square root of 3. Square root of 3 times 5 is positive 5 square root of 3. And then square root of 3 times negative square root of 3. Positive times a negative is going to be a negative. What's square root of 3 times square root of 3?
3.
3. What happens here in the middle?
They cancel.
They cancel, don't they? So those go away. So my answer then would be 5 minus square root of 3 over 25 minus 3, which is going to be 22. So there's my answer. I've essentially rationalized the denominator. I've gotten the square root out of the denominator, but the value of this is the same value as that.
How does that go to 5 minus square root of 3?
How does it do that?
You cancel out those two and you have 25 minus negative 3. How does it go to 5 minus square root of 3?
No, the negative goes to 5 square root of 3, so those cancel out. That's what. Those
So this is the numerator? That's the
So then it's
numerator?
25 minus 3.
Same idea here. I need to get square roots out of the denominator. I'm going to multiply by the conjugate, which is going to be the square root of 6 minus the square root of 2. And I need to multiply that in the numerator and the denominator. So when I do this in the numerator, I need to distribute my 3. So I'm going to get 3 square root of 6 minus 3 square root of 2. And then in my denominator, square root of 6 times the square root of 6 is what? That's just 6, right? 6 times the negative, square root of 6 times negative square root of 6 is negative. Guys, if they're both square roots, we can multiply them. So I'm going to call that negative square root of 12. Square root of 2 times 6 is going to be positive square root of 12. And then lastly, square root of 2 times negative square root of 2 is going to be negative 2. So again, these will cancel. In my numerator, I have 3 square root of 6 minus 3 square root of 2 divided by 6 minus 2 is 4. Questions so far? Sam?
Would you be able to combine 3 square root of 6 with 3 square root of 6?
Okay, I'll answer that question right down here. It's a great question. Sam's question is, hey, can we combine these? And the answer is no, because moving down here, in order to combine things, they have to have the same square root. They have to have the same radical. So in this case, don't I just have 1/4 root of 10 here?
Yep.
Are you done? Are you done?
I'm just trying to
Oh, probably shouldn't have music on when I'm teaching. So, well, I have 1 of them plus 7 of them. Isn't that just 8 of them?
Yep.
So 8/4 root of 10. Tristan, let's have our headphones off. There's no way you can listen to music and listen to me. Again, here I've got 8 to the 1/5 power. Well, I've got 2 of them and 10 of them. That's 12 of them. Now, so going back up to Sam's question, can I combine these? And the answer is no, because they don't have the same radical. This essentially is like 3x minus 3y. I can't combine them. They're different. Now, if I look at this guy, this one's a little bit different because I don't have the same square root. But here's my question. Can I simplify that radical? Meaning, is there a perfect cube inside 54? The answer is yes. It's 27. So I can break this up and say the cube root of 27 times the cube root of 2 minus the cube root of 2. Now don't do this. Can I just cancel these? It's that minus that. Can I just cross them off?
Yes.
Why not, Sydney?
I can't explain it.
Yannick? I've got a multiplication sign. Those guys are hooked together. Okay? Those guys are hooked together. What's the cube root of 27? Careful. 3. So I have 3 cube root of 2 minus cube root of 2. Okay? Now here's my question. Can I subtract them now? It's connected, but would you agree that there's just a 1 there? Okay? So I have 3 of these minus 1 of these. Doesn't that give me 2 of those? Oops. Yeah, that's right. What a common thing people will do, they'll see this and they'll just cross them out. They'll say, you know what, I'm going to cross that guy out with that guy out, and there's my answer. Well, that's not the case. Okay, so simplify this first. 3 of them minus 1 of them, hey, that gives me 2 of them. Okay, last part. Simplifying these radical expressions. I have a sheet of paper somewhere. So if I look here, is 64 a perfect cube? Cube, because it's the cube root of 64. It is, isn't it? What about y to the 6th? Is that a perfect cube? And here's how you know. I'm looking for exponents that are factors of 3. Because if you think about that, you don't write this down, but if I did the cube root of y to the 6th, I'm asking myself, what times itself is y to the 6th? Isn't that y squared times y squared times y squared? So, a helpful hint is, hey, I'm looking for exponents that are factors of 3. So the cube root of y to the 6th is y squared. So this final answer, the cube root of 64 is 4. The cube root of y to the 6th is y squared.
And that's the answer.
And that'd be the answer.
So you would just divide those two.
Essentially, yes, you are dividing.
Like you divide the 6 of the y and 3. Is that
Yes.
okay?
Yes. Okay? Now, is 8 divisible by 4?
Yes.
It is. What about 14?
No.
It's not, is it? Okay, so here's what I want you to do. I want to break this up. 4, well, we can't do anything with 4. A to the 4th is good, A to the 8th is good because 8 is a factor of 4. Now, when we get to our b's, 14 is not good. But check this out. What if I called this b to the 12th and b squared? Would you agree that now I've kind of broken it into something that can be simplified? That b to the 12th now can be simplified. And what about c to the 5th? That can't be. So I'm going to break that up in c to the... nope, because I want it to be factors of 4. So c to the 4th and c.
You're just rewriting that problem, right?
Yeah, and guys, I think it's going to be easier if I show it this way. Erase that. Erase that. I want to do it this way. I want to think about having all of my perfect squares over here and all of my maybe not so perfect ones over here. Is 4 a perfect 4th root? No. So that's going to go over here. It's like my perfect square, perfect 4th roots and my leftovers. 4 is going to go over there. Is 8 to the 8th? Yes, I'm going to put that guy right here. Now, b to the 14th we've said isn't, but b to the 12th is, and then I have a leftover of b squared. And again, c to the 4th, c to the 5th isn't, but I can do c to the 4th and c. So what this allows me to do is to simplify the things that can be simplified. So the 4th root of 8, a to the 8th is a squared. Essentially, like Cole said, we're dividing. B to the 12th, and take that, the 4th root of that, is going to be b cubed. and I will have c times the fourth root of, again, this is all my leftovers, so I can't do anything with that, 4b squared c. So break it up into perfect, in this case, fourth roots and leftovers, and we can simplify our perfect fourth roots. I have one more here. Put it somewhere down there at the bottom.
You would just bring that down with it. Just multiply would just have it in that.
Say it again.
Like you just bring down those leftovers, like you said you were, just bring them down.
Correct.
Okay.
Kind of, it goes all the way back to this stuff, Cole. Oh, all the way up here. Hey, when I broke the square root of 32 down, I broke it down into a perfect square, and it's leftover, essentially.
Yeah.
And that's just got to stick around.
All right.
Okay, last one. Cube root of, it's going to be a fraction, 27 x to the 6th y to the 9th over 64 z cubed. What do we notice here? All the variables are perfect cubes. What about 27, 64? Everything is a perfect cube in here, isn't it? So I'm just going to do the cube root of everything. Cube root of 27 is 3. Cube root of x to the 6th is x squared. The cube root of y to the 9th is y cubed. Cube root of 64 is 4. Cube root of z cubed is z.